Hello, I am Vishal and I am presenting analysis of planar multilink cable-driven robots using internal routing scheme. In recent years, there has been an increasing interest in robotic and other mechanical systems actuated or constrained by cables. In such systems, an individual constraint is applied to a body of the mechanism in the form of a pure force, which can change its magnitude but cannot reverse its direction. The unidirectional actuation complicates the design of cable-driven robots and can result in limited performance. The primary objective of this work is to develop models for multilink cable-driven robots with arbitrary routing topologies. The objective of the work are driven by questions. In particular, modeling of MCDRs with different routing topologies are investigated. In studying the proposed objectives, this work makes the following contributions. Single-link cable-driven parallel robot SCDRs represent a single link that is actuated by a parallel configuration of cables. These manipulators can be seen as parallel manipulators in which all rigid links, with the exception of the end effector, have been replaced by cables. As a result, SCDRs are typically described in terms of number of cables and joint types such as revolute, planar, spherical, and spatial. CDPRs with multiple rigid links are termed as multilink CDPR, otherwise called as MCDRs. The kinematic modeling of MCDR is presented. Allowing cables to be routed through multiple links, each cable consists of multiple cable segments. The kinematics of a cable with multiple routing points can be described by segment vectors. Due to the existence of interlink constraints, the tensionability of MCDR is a problem of higher complexity. Similar to cable-driven rigid body system, the equilibrium equations of a serial multi-body chain can be derived. Unlike the rigid body case, the MCDR contains constraint wrenches too. For a single revolute joint controlled by two cables, part of the external wrench will be balanced by the constraint in the joint. If we use Newton's method, the internal reaction forces or moments between the bodies must be explicitly considered and then eliminated. The large size is due to the Newtonian formulation of dynamics. Using Lagrange's approach and notion of generalized forces eliminates the internal unknown forces or moments from the equations. The wrench closure workspace is defined as a set of poses in which the manipulator can sustain any arbitrary external wrench. The WCW can be calculated inspecting the null space of cable structure matrix or using hyperplane shifting method. Here we use null space method to extract the tensionable surface boundaries and evaluate the wrench closure workspace. The symbolic expressions of structure matrix for 2-link planar and 3-link planar MCDR are presented. The cable routing type refers to the path that a cable routes through the links of a cable-driven serial kinematic chain. A proximal link refers to greater closeness to the base in a serial chain, and a distal link refers to the greater closeness to the end effector. Here, the external routing is the routing of cable with an end fixed in a link through each proximal link passing through points fixed in links. An internal routing refers to rerouting of a cable between two points in the same link. Different schemes are shown in the figures. The direct connecting scheme refers to a routing scheme where the actuating cables directly connects one of the links to the base. And the internal routing scheme refers to a scheme where the cables are routed internally in addition to being externally routed. Grouping of independent cables from the base is called as a bundle. The pass-through scheme is a scheme where the cables are co-shared between multiple links. By using cable routing between links, rerouting, and cable bundles, it is possible to actuate any multilink cable-driven robot. The kinematic modeling of MCDR with routing scheme is presented. To understand the effect of cable routing, let us look at the scenario of the torque generated at respective joints due to cable 1. Considering cable 1 attached on link 2, one can model the contributed torque at joint 2 due to cable tension force T1 as L12 dou R2 by dou theta 2. Here L12 denotes the second segment of cable 1, which is the vector from attachment point on link 2 till link 1. The joint torque contribution due to cable 1 on joint 1 is given as the combination of two terms, where the first term signifies the torque contribution by cable 1 on link 1 and the second term gives the torque contributed due to the routing of cable 1 that is passing through link 1. The wrench closure workspace of 2-link planar MCDR with direct connecting scheme is presented for n+1 minimally actuated and 2n maximally actuated cables. The joint space and the end effector reachable area plots are shown. The end effector reachable area is maximal for cable configuration with 2n number of cables. The end effector reachable workspace is primarily along the boundaries and across the origin for n+1 cable configuration. Analysis was performed for tooling planar multilink cable-driven robot with pass-through routing scheme. There is a loss of workspace in pass-through scheme, and the reachable workspace is primarily along the boundaries and across the origin. This is due to the fact that the routed cables results in actuation of link 1 even when minimal actuation of link 2 is required, leading to the instability in joint 1. The point where the cable is routed through link 1 serves as the actuation point for link 2. It is unable to generate enough momentum for link 2 to get actuated as the point is closer to link 1. By increasing the offset distance of attachment points, the workspace can be improved. As you can see here, the end effector reachable area for 2n cable configuration is higher compared to the n+1 cable configuration using pass-through scheme. One of the workspace metrics which will be used to quantify a given robo configuration is the end effector reachable area. By applying the robot's forward kinematics to the allowable joint angles, the Eeri metric can be found. The linear programming problem formulation is as follows. The objective function minimizes the sum of all cable tensions such that each cable tension falls within the lower and upper bounds of cable tension. Due to the nature of linear programming, discontinuities are produced. The solution of LP problem is always at the corner of the convex hull of a feasible set, and when the solution changes corner during motion, discontinuity occurs. Due to this concern, the quadratic programming approach is performed, as it can provide continuous cable tension trajectories. Similarly, the analysis is performed for the 3-link multilink cable-driven robot. The internal routing configuration required less cable tension than the traditional 2-1 design, and this is subject to choice of attachment point and routing. The cable tension plot and the joint workspace plots are shown. The tension factor provides a task-independent description of the actuated force distribution in producing arbitrary wrench. When the tension factor approaches to 0, the mechanism is located near to the workspace boundary, and if it approaches 1, the mechanism is positioned far away from the workspace boundary. Larger value of TF implies a balanced tension distribution among the cables. In conclusion, the kinematic and workspace analysis of planar multilink cable-driven robots was performed, and different cable routing schemes were proposed and which led to the different tensionable workspaces. Highly coupled actuation by allowing cables to internally route through the link to create new cable configurations was presented.